Okay, I'll be going through the assignment E1 now. So what you will do is that you can practice the question first and check through the video, or you can follow me as we go through the assignment and then you attempt the questions. All right, the screen should be showing the assignment E1. So I will go through every question one by one so that you will be able to check your answers and then make your corrections, or you follow me through as we solve the questions. Okay, so there are 14 MCQ questions. Which is the best definition of standard state? So over here, standard state comes about when we were talking about enthalpy change of formation. So formation is when you form one mole of a substance from its elements in their standard states under standard conditions. So that's when we first encounter the word standard state in the notes. So what is standard state? So if you refer back to what I mentioned, standard state at standard condition. So it's the state of the substance that is naturally found in when we apply at standard conditions. So you need to first, of course, know what is standard condition. So standard conditions here is not STP. I think I've said many times. I'm going to say one more time again. Standard conditions for energetics does not refer to STP. Okay, standard conditions here refer to room temperature of 298 Kelvin and any gases at a pressure of 1 bar. And if there's any aqueous solution, is at 1 mole per dm cube. That's a standard condition for this topic. So let's read the options. Standard state of a solid is the most pure form of solid. It's like not much information there. Standard state of a solid is the most pure form of the solid at 298 degrees Celsius. The standard state of the gas is the most pure form of the gas at 298 degrees Celsius. And the standard state of the gas is the most pure form of the gas at a pressure of 100 kilopascal. So which is the most correct answer? So if you look carefully at B and C, they look like they are the answer, but look at it carefully, the units, this is 298 degrees Celsius, not 298 Kelvin. And therefore, the answer for this question will be D. Okay, 1 bar is actually 100 kilopascal. So therefore, for gases, we only focus on the pressure. So the pressure will be at 1 bar, which is 100 kilopascal. Okay, so that will be for question 1. Next, we look at question 2. For question 2, what is the question trying to show you is that you need to interpret the energy profile diagram and understand that it's trying to show you an endothermic graph. Okay, so you are seeing an endothermic graph. So your job here is, of course, to look at the different reactions or processes that is given and see which is endothermic in nature. Okay, so I'll give you some time to take a look first. So the first processes involves breaking all the bonds to form atoms, which is atomization, but atomization of a molecule. Second process looks like hydrogen formed with oxygen. You can actually interpret it as a combustion. Okay, but it's not enthalpy change of combustion because you did not burn 1 mole, but it's an overall combustion process. Third one is also a combustion process because you can see you are burning methane. So in a way, it's a combustion process. And the fourth one, you are combusting carbon to form carbon dioxide. So it's a combustion process. So combustion nature will be all exothermic, and therefore the answer is A. All right, question 2 done. Now we will move on to question 3. So for question 3, so if I have this amount of water is added to this amount of water, what's the final temperature? Of course, some people will guess. But this one, a little bit hard to guess. You can guess to eliminate some options. So if we are mixing equal amount, 25 and 25, then it will be in the middle. It will be 40. But now I'm mixing more hot water than cold water. So it will go towards the hot side. So we expect it to be an answer more than 40. More than 40. So these two out. So it's either 50 or it's 60. Okay? So let's say we chose this. You can do guess and check at this point. So let's say final temperature is 50. Let's say final temperature. I choose 50 and I try first. So the formula of heat loss is equals to heat gain. So mc delta T equals to mc delta T, right? So C and C is the same, so you can actually cancel it out from the picture, so no C. All right, so now put in the value. M, what is M? The heat loss is by the hot water. Heat gain is by the cold water. So heat loss by the hot water is, M of hot water is 25. Delta T is not T, it's different. So it's 80 minus 50. So I'm doing guess and check. I check with 50 first. Then the other side, cold water is 15 grams. And delta T, I do guess and check. So it's like 50 minus 0. So 50. So you press your calculator. If my left-hand side equates to right-hand side, then that's the answer. But if it's not the answer, then the left-hand side will not equal to the right-hand side. So you press your calculator for the 50, and then you do the same set of guess and check if you want to for 60. So it will be like 20, 80 minus 60 equals to 15, 60 minus 0. So you see which batches. Okay, I'll show you the answer for the 60. So it's like 25 times 20, so I get 500. Then the other is 15 times 60, I get 900. So I purposely show you one that doesn't match, so you can understand why the answer is 50. Okay, so answer is C. Okay, that is for question 3. Now we are going to question 4. For question 4, you are given some metals with specific heat capacity, and they ask you this amount of heat is added to 10 grams of sample, which are all at the same initial temperature. Which one will end up? Have the smallest temperature change. Can you put in the word change? You must have the smallest temperature change. All right. So if everything is the same, amount of heat is the same, initial temperature is the same, everything is the same, then the only thing that matters is the specific heat capacity. So we need to understand what is specific heat capacity. It is the amount of heat energy needed to increase the 1 gram of a substance to raise its temperature by 1 Kelvin. So the more it requires to raise it by 1 Kelvin, then the 100 joules will only result in a smaller temperature change. So therefore, for question 4, the one that will give you the smallest temperature change will be the one which has the highest specific heat capacity. So answer will be magnesium B, because it has the highest specific heat capacity. So it takes more energy to just create a temperature change of 1 Kelvin for 1 gram of substance. Okay, next we are at question 5. So when this amount of acid is react with this amount of base, the temperature increases by 13.7. Calculate the enthalpy change per mole of product. So this is 0.05, this is 0.05, mole ratio, this is 0.05. So we know N, sodium chloride, is 0.05. Now next, the temperature increases. So based on this idea of temperature increases, work out whether it's an exo or endothermic reaction first. So if you are aware, since temperature increases, you are giving out heat. So giving out heat, we are expecting answer will be either A or B. So we apply our calculation, Q equals to MC delta T? No, we can't because they say heat capacity was so much. Now, can you say the heat capacity of the system doesn't have a mass? It's usually joules per gram per Kelvin. Right, just go back to the previous question, joules per grams per Kelvin. So this one, we will just take that the whole system, the mass. So this is actually already MC. It's not specific heat capacity, it's heat capacity. So heat capacity is not specific heat capacity. What's the difference? Heat capacity is joules per Kelvin. Specific heat capacity is joules per gram per Kelvin. So the gram is already factored in. So what's the relationship? Heat capacity is actually specific times mass. So your M, C is already together. So we give it a symbol. The common symbol to use is a capital C, big C. That is a small c. Okay, so the formula will be C delta T. Okay, so Q equals to C delta T. This is a capital C, the heat capacity C, not the specific heat capacity C. So this heat capacity is 209.2. Delta T is 13.7. So with that, you work out what will be the best answer for C delta T. It will be A. Okay, that's for question 5. Now we are moving on to question 6. So for question 6, everything looks like the same. If you look carefully, you will see that the difference is here. This is 100, this is 50. Now, but it doesn't matter because the sodium hydroxide will limit the reaction in a way for both sets. So the limiting reagent, if we say let it be sodium hydroxide, so even I have more HCl, but it's not going to react. So the extent of the reaction is going to be the same for both. Okay? The extent of reaction is going to be the same. So we expect the same amount of heat given out. But there's something that is different. The volume or the M is not the same. So the M for this case is 100, whereas the N for this case is 150. So if Q equals to MC delta T, if Q is the same for both sets because of limited by the sodium hydroxide, when M increases for experiment B, that means T has to drop. So with that, choose the correct answer. All right, think through which is the correct answer. Highest temperature is lower than B. In fact, it's going to be higher than B because the same amount of heat hitting a smaller volume, so it should be higher. The highest temperature is equal, so it can't be equal. The amount of heat in A is lower than heat in B. No, the heat is the same because of limited by sodium hydroxide, so heat is the same. Wrong. So answer is D for question 6. So question 6, the answer is D for dog. Question 7. Now look at question 7, which represents the delta HF or sodium chloride. So formation of 1 mole of the compound in standard state under standard condition from its elements. This is not 1 mole out. This is not 1 mole out. This is not element. These are not element out. This is also not element, so out. So the answer is A. So we are forming from elements. Next. So that's for question 7. Now we will go to question 8. Now, question 8, very straightforward, algebraic manipulation method, because equations are all given to you nicely. So I have equation 1, 2, 3, and 4. Fit your equation 1, 2, 3 to fit 4. Okay, try out first. All right, so look at common terms and whether they are on the same side, same mode. So the two questions that we always ask ourselves will be, are they on the same side? Are they about the same modes? Okay, so carbon and carbon, I'm seeing carbon here, I'm seeing carbon here. Carbon are on mode. Sorry, I repeat that because of the mute effect. Carbon and carbon are on the same side, but they are not of the same modes, right? So therefore, what must we do to this? We need to multiply by 2. So minus x must multiply by 2. So 2, 2, 2. So I've done equation 1. Now I'm going to do equation 2. So equation 2, hydrogen and hydrogen are on the same side, but not the same number of moles. So what I should do to equation 2 is I need to multiply by 3. So multiply 3, 3, 3, minus y times 3. Next, I'm saying C2H6, but the C2H6 are on the wrong side. So in my mind, I flip the equation, and therefore I will flip the sign to positive Z. Then take a calculator, add up everything. So if I add up everything, it will look like this, minus 2x plus minus 3y, which is minus 3y, plus z. So minus z is plus z. So you look at which one give you the same response, minus 2x minus 3y plus z. And that will be the answer, C. So that's for question 8. All right. Now, question 9. So for question 9, which of the following reactions can the bond energy of OH determine? Using only standard enthalpy change of the reaction. Only can use that. So bond energy is about breaking something into atoms. Break the bonds, form atoms, right? So you break the bond, you form atoms. So you must break the OH bond or you form the OH bond. So A over here, although there seems like one bonds breaking, but there are also bonds forming because we are seeing some H2 and O2. So wrong. So those that have found bond forming, wrong. For over here. Not really because they are bond forming, but because you see, I break them into atoms, then I reconstitute them. So it involves bond breaking and bond forming, both process. So it cannot really accurately just find out the bond breaking aspect or the bond of the OH aspect. So let's look at number B and C. So B, right, I think atoms, they are already in atom state that I've joined to form the molecule. So I am forming the bonds. So it's only one way, forming the bonds. And I'm forming 2 OH bonds. Like in water, I'm forming 2 OH bonds, 1 bond, 2 bonds. So after that, I can divide by 2. I can find the bond energy. Okay, so B looks like the promising as the answer. C also looks quite promising. H2O, so this time I have H2O, but I break it up, and I'll get atoms. It's back to atoms. So this one, B is bond forming, C is bond breaking. But there is a difference between the two of them, is the state symbols of the water. So bond energy must be gaseous. So therefore, the answer will be B for question 9. All right, for question 10 now. For question 10, we are applying bond energy to calculate something. So if you still remember, the formula will be delta H reaction equals to bond energy reactants minus bond energy products. Okay, bond breaking minus bond forming. So there's a H bond, there's a Br bond, and there's a 2H Br bond. So take the reactant minus the product, sum of the reactant minus sum of the product. So the reactant will be HH436, right? Besides that, also need to add in bromine. So 436 plus 193, that's for reactant. Then you minus the product. Product will be 2 times 366 because there are 2 HBr. Now, take note to always bracket your answer or make the calculation separate so you will not lose all your marks if it's a structured question. So if it's a structured question, show me the working for the bond breaking, show me the working for bond forming, then calculate. If not, you have to be clear enough to have a formula written like this one, right, for me, and show me using brackets the computation of bond breaking and bond forming. All right, so calculate now using your calculator and you'll find the answer is C. That's for question 10. Next, we are going to question 11. Enthalpy change of formation is this. Enthalpy change of atomizations are this. What is the average bond energy? This is a quite difficult question. Okay, because why? Everything is given to you in words. But if you can translate the information into equations, then you can use a manipulation method. Even if you want to draw Hess's law method, you will also need to translate it into equation. Okay, so I'm going to translate every information into equation. First one, formation this. Let's do it. So formation CCl4 gas minus 610 formed from elements. So C plus 2Cl2 gas. So C solid plus 2Cl2 gas forms CCl4. So that's the first equation in the line in blue. Second, the equation in the line in green. Enthalpy change of atomization of carbon. So atomized carbon is to form from solid carbon to gaseous carbon. So atomizing the carbon is class 448. That's equation 2. Equation 3 is the one in pink. Atomization of chlorine. But atomization of chlorine is from a molecule into atoms. Form 1 mole of atom. 1 mole, 1 mole. So I can't write this, people. We can't write this, can't write this. Okay? I have to be 1 mole, and therefore this has to be half. So half chlorine, give me chlorine gas. It is plus 122. Atomization 3. Okay? And then they say find average bond energy, CCl. So we need to have an equation for the bond energy, which is the last one, bond energy. Okay, so let's write it out, bond. That's what I'm supposed to find. So bond energy of CCl. So if you look at CCl4, the question is CCl4, right? You see, in order to get bond energy, I actually break 4 bonds. But that's not bond energy. I need 1 bond only, right? So I'm just going to write up based on the 4 bonds first to let you see CCl4. Gas, based on definition, gas must be gases. Then you break, and then you get atoms. Then you get C gas atom plus 4Cl gas atoms, right? But that is not atomization. That is not bond energy of a CCl bond. That is the bond energy of 4CCl bond, right? That is bond energy of 4CCl because I break 4 bonds to get to here. All right. Then how you can say, oh, madam, then do this, then do this. Madam, do this. Then break 1 bond, right? Yeah, break 1 bond. But is this average? No, it's not average. And also, there's no common term CCl3 to match with people. I mean, you can try to do this, but I would prefer to, you can try and see, get the same answer, but I would prefer to do this way. And since it involves breaking 4 bonds, then I will let 1 bond energy be X. Then this will be, the energy change will be 4x. Right? So whatever energy I get, then I divide by 4. So the answer for this equation 4 is 4x. So you want to find x, I divide by 4. Okay, so look at the equation. So this is what I'm supposed to find. I'm going to find out the 4x first, then find x. Okay, so looking at equation 1 and what I have, what is the common term? It's not the carbon. Some students for other class tell me carbon. It's not a carbon. The carbon is solid. This carbon is gas. So it's the CCl4. The CCl4 is on the wrong side, but the same moles. So change it to positive. Okay, the second one, the common term will be C gas. Same side, same moles. Let it be. Cl, same side, but wrong moles. Over here, for me, I did 4 by 4. So, I mean, of course, you say that, oh, but madam, later I times 4, later you divide by 4. Okay, but I mean, I will just multiply by 4 first to make it easier. So, 2, 4. But if you don't want to do this way, you want to do another way, then up to you, okay? So, I will sum up everything. 610 plus 448 plus 122 times 4. Okay, I get 1, 5, 4, 6, and that is 4x. So then I'll just divide by 4. I have to get x is about 386.5. Right? So bond energy is defined as energy needed to break the bonds. So the answer in this case, because it's an average bond energy, I do the averaging by dividing by 4. So my answer is C. For question 11. Okay, question 12. For question 12, for HR student, you learn it under Born-Haber cycle. You also learn it under chemical bonding when we do ionic compound. Okay, when we talk about the lattice energy of ionic compound. So lattice energy is proportional to the product of the charges over the sum of the ionic radius. So you can't remember the equation, still not too bad. You just need to know that charges is a numerator and the radius is the denominator. That's all you need. So it's trying to tell you that lattice energy is directly proportional to charges and in a way like a bit like inversely related to the sum of the radius. Right? So we want charges to be big and we want radius to be small. So if you look at this, R, B, F, CS, CL, or CSF, all of them have the same charge, plus 1, minus 1. The only difference is the radius. So let's put it in order. R, B, F, negative 760, CS, CL, negative 650. So you need to know where are they in the periodic table in a way. You need to know which is smaller and which is bigger. So if you go to your periodic table, then you will be able to see that CS is actually bigger than RB. So CS is bigger than RB, right? So if CS is bigger, then that's why its lattice energy is lesser in terms of energy evolved, because its lattice energy is inversely proportional to sum of ionic radius. So because this is larger. So the question says, where would you in a way put CSF? So if I have a CSF which is larger than RB, so it has to be lower than RB, less exothermic than RB. But because the F is smaller than CS, so there are only two places that you can put there. You can put here, here, or here. Right? So it is, because its size is bigger than RB, I will not put it in front of RB, means it's even giving out more energy. It will be lesser than RBF, but it will be more than CL. So I will not remove here. I will not put it here because it's smaller. Right? So the larger radius is towards this side. Okay? So I will put it here. So I'll expect it to be a value that is in between 760 and 650 for question 12. So I will choose B for 720. All right, next question, question 13. Now, question 13, you will look at the question. It's trying to tell you that the conversion is highly favorable because it's an exothermic reaction. You don't need to supply heat to get the reaction. In fact, the energy gives out heat, The energy gives out heat and the energy proceeds towards greater stability. Okay, the final product is even more stable than the initial diamond reactant. So it proceeds towards better, lower energy product is more stable. So it should happen most of the time. But it's not happening, or I'm not seeing it happening at room temperature. Because why? Because it has a high activation energy. So it has nothing to do with other reasons, but because it has such high activation energy that even though energetically it doesn't require you to supply energy for the conversion, but the activation energy makes it very hard for the reaction to start because you need to overcome that. All right. Now, next question, question 14. So over here, you have some equations. They ask you calculate conversion of oxygen to 1 mole of ozone. So write that equation out. So oxygen to 1 mole of ozone. Some students very tempted, oh, madam, 3 and 2. No, because 1 mole, right? So we have to make it into 1. It has to be 1. And then, therefore, this would be 3 over 2. Which is 1.5. To get me 3 oxygen atoms. Okay, so then follow the equation. O2, are they on the same side? Wrong side and wrong mole. So flip this to become minus 566 times 3 over 2. Wrong side, wrong mole. Then the next one, ozone, is it on the same side, same mole? Ozone is on the wrong side, but same mole. So plus 992. Then take a calculator and work it out. Minus 566 times 3 over 2 plus 992. And then you see what do you get? I'll get 143. C as the answer. Okay, so that's for the MCQ section. So then later we'll be looking at the structured questions. It's really quite long for the structured question. So I will go through selected structured questions. For example, I will go through different type of questions. So I will go through question 16, which involves the use of bond energy. Question 15, which is a bit different. Question 17, there's a atomization, and question 19, whereby you use HF. Question 20, you use HC, and maybe just one of the calorimetry questions. So likely I will be going through the one that is more difficult than question 21, which is so long. Okay? So question 15. So question 15, they says that the formation of MgO is minus 602 and Al2O3 is minus 1700. Calculate the enthalpy change. So we are giving formation data. So formation and formation. So it's very straightforward. Just products minus reactant. Products minus reactant. So this is product and then this is reactant. So the formation will be delta H reaction will be 3 times the MgO minus 602 minus the reactant, which is Al2O3 minus 1700. Now, why are we ignoring all this? Because they are elements, right? So our working will be 3 minus 602 minus 1700. Then press your calculator, see what you get as the answer. So 3 times negative 602 plus 1700. So I get my answer negative 106 kilojoules per mole, or kilojoules for the reaction. So what is another data that I need to determine if I want to see whether magnesium will reduce something? So if I want to know whether something will react with something, then I'm asking myself, do you know it's spontaneous or not, right? Because if this will react with this will reduce, this means I'm asking myself, is the reaction spontaneous, right? Spontaneous or not? So if I want to know whether a reaction is spontaneous or not, then the best way is you give me the delta G value. If you give me the delta G value, then I can tell. Okay, you give me the delta G or the delta G theta value, any of or the delta G theta value, that I can tell from the sign. Because a spontaneous reaction will have a negative delta G theta or delta G value. So if it's a negative value, then I will know that it's spontaneous. Okay, so the other data that you need for question 15 is delta G. That's for question 15. Now we go to question 16. We are going to find the enthalpy change for this reaction using section 12, which is the bond energy, right? Bond energy table. So go to section 12. So usually for bond energy, the habit is always to draw it out. Okay, you must have the habit to draw it out. So draw out so you can count your bonds properly. Don't do shortcuts and then think that you can visualize organic chemistry. So you tend to make more mistakes that way. So if you draw it out, okay, so then you can count your bonds. Here you need 1, 2, 3, 4, 5, 6. 6 CH bond. Here is 1, 2, 3, 4, 5, 6, 7, 8 CH bond. So 6 CH bond, 8 CH bond. This one C single bond, 1 C double bond. This one, 2 C single bond. All right, and then here you have 1 H bond from the hydrogen. So sum up the bond energy on each side. So go to the data booklet table 12 and sum up bond of the reactants, bond of the products. Try to separate the working. I can tell you many times to try to separate, but if you don't do it, I also can't help you. Okay, so go work out from the bond energy. Oh, the HH is how much, the CH is how much, and sum up. All right, so it will look something like this. 6CH. If I'm going to look at reactants minus product, there will be 6 CH bond. So the CH bond is 414. So 6414 plus 1 CC bond 346 plus 1 double bond, which is you get from below, which is 614. Reactants minus product, so plus HH bond 436 minus products 8 times 414 plus 2 CC bonds, which is 2 times 346. So 8414 plus 2 CC bond. Okay, then you work out what do you get. So you net off 1 bond energy. Okay, work out the calculation. So here I have 3880 and here I have 4004. Then you calculate 380 minus 404. you'll get negative 124 kilojoules. So the energy, the enthalpy change of this reaction is 124 kilojoules per mole for question 16.